Hi everyone, this is Cyril from AML and my topic is Finite-State Machine Motion Controller. Introduction. Digital controllers are used for modern power converters, control and industrial automation. The functionality of the finite-state machine provides an ideal platform for building a high-frequency field programmable gate array controller for power electronic application. The main design specifications are robustness to load and electrical parameters, fast dynamic response, reduced switching frequency, and simple hardware implementation. A discrete event type controller is proposed to meet previous specifications designed as finite state automation and implemented with an FPGA device. Furthermore, the actual controller architecture is based on the FPGA's pattern 3. The experimental results are presented using a brushless AC motor as the converter's load. However, this does not limit the wider applicability of the proposed controller as it is suitable for different type of AC load rectifiers inverters. The introduction of switching pattern sequence can be a good alternative for switching frequency reduction. The dominant existing motion controller architecture completely separates the amplifier and servo feedback loops. The inner current feedback loop is implemented inside the amplifier as either linear regulation or pulse width modulation. The linear amplifier tends to have sufficient bandwidth but may experiences crossover distortion when reversing motor polarity, and they exhibit relatively high amplifier heating. PWM amplifier removes excessive amplifier heating because the output transistors of metal oxide semiconductors feel effects. Transistor MOSFETs are fully turned on or off. Also, the digital nature of PWM amplifiers is attractive to modern designers with single chips providing much of the necessary logic when switching at 20 to 80 kHz. However, these amplifiers shows a residual current ripple at the switching frequency, the introducing electrical noise and possibly sufficient switching frequency introducing electrical noise and possible sufficient motor heating bandwidths of most PWM amplifiers fall within the range of the several hundred hertz to a few kilohertz, well below the switching frequency. In recent years, there has been considerable interest in the development of control act concept and algorithms for complex processes that are characterized more by the occurrence of discrete events than by difference equations representing the laws of physics. Such processes are typically man-made, flexible manufacturing systems, computer networks, and are often best describing in the symbolic rather than numeric form. Our goal is to combine concepts from both computer science and control to develop a meaningful theory for controlling power electronics and motion drive systems. In particular, the model and formalism used in this system comes from the field of computer science, automata, FSM, synchronous process, while the problems and design paradigm comes from the control, stability, regulations, robustness, etc. FSMs also known as the finite state automata as the simplest or model of system behavior with a limited number of defined conditions or modes where more transaction changes according to circumstances. A, an FSM is typically used as a type of control system where knowledge is different in the states and actions are constrained by rules. An FSM consists of four main elements: the states that defines behavior and may produce actions, State transactions that are movements from one state to another. Rules or conditions that must be made to allow for a state transaction and trigger events that are either external or internally generated and may possibly trigger transitions. The interface performance the rules of facilitating communication between the two different layers by translating signals between them. The two layers which is discrete event system these can different type of descripting language such as FSM, fuzzy logic, Petrinet, etc. The bottom layer is the continuous system and representing the black matter, the dynamics of which can be described with the transfer functions or differential equation. The interface performs the role of facilitating communication between the two different layers by translating signals between them. As the techniques for control design and analysis become well developed for continuous and discrete system, the design of the interface is of utmost importance because it determines the manner in which the combined system behaves. It will be based on the FSM in combination with the ECA rule. The design of the slide mode system. The switching manifold system should be selected in such a way so as to guarantee the desired system performance while the control should be selected to ensure that the performance motion is forced to stay within the sliding mode manifold. Mathematically, the above mentioned procedure may be presented as follows. From the system specification selected the vector value functions sigma equal to sigma of x power d comma x where x power d represents the desired changes in the control vector variable x so that the design specifications are met if the closed loop system is constrained to belong to the manifold m equal to x tends to x sigma equal to sigma of x power d comma x equal to 0. The control input should be selected so that the stability of the solution sigma equal to sigma of x power d comma x is guaranteed. The simplest approach is to use the Lyapunov based design in such a way that the control is designed from the line of stability condition. Continuous black motor control. The black motor combination many of the advantages of the permanently existed AC motor and the synchronous motor. The black motors need a low reactive current, which is very similar to the AC motor, and the current is proportional to the torque to the shaft torque is therefore easy to estimate by detecting the three-phase current of the black motor. The black motor is a combination of the permanently existed synchronous motor and the three-phase inverter. The black motor dynamics are described using the differential sequence for motor current. The FSM current controller in this control strategy measured load currents are compared with these differences using hysteric comparator. Then the resulting controller will be discontinuous and the sliding mode manifolds will be reached in the finite time. Each comparator determines the switching state of the corresponding inverter like scale of S1, S2, S3 that the load currents are forced to remain within the asterisk band. The performance of the asterisk controller is good with a fast dynamic response. Due to the interaction between the phases, the current error is not strictly limited to the value of asterisk band. This switching frequency changes according to variations in the load parameters and operation conditions, which is one of the major drawback of the strict control since the variable switching frequency can cause a responsive problem. Here the states has given the Vk plus 1, V of k plus 1, V of z, V of k minus 1, and this is the transitions. Here the dark line represents the changes, and the red line represents the changes, and the green line represents the changes voltage sector. The FSM is the represented state transition diagram of VSI current controller. The state V of k represents the input voltage vector and V of k of three-phase inverter. For each voltage sector of the black motor voltage is USI. V of k represents the active voltage sector. V of k minus 1 is the previous active voltage vector. V of k plus 1 is the possible future active voltage vector, and V of z is the producer zero voltage vector of the VSI. FSM supervisor implementation and production. The proposed approach is based on parallel processing and is suitable for FPGA implementation, such as implementation. It would be possible to reproduce a new more ideas switching mode process, current amplitude, motor speed, DC link and motor temperature are monitored by the supervisor. The supervisor can affect this parameter and the difference values when any of the measured value is critical. Conclusion. This system addressed the FSM controller of black motor and the problems of speed and current controller. The two layer of controller architecture were combined into continuous time and is the FSM part was implemented using an FSM under ECA rule. Events identification, including other conditions, was most important for executing action. The nonlinear behavior this system limited the performance of this conversion historic controllers that were used for comparison. The simulations and experiments confirm the potential of the presented FSM approach. The switching number of the three-phase inverter was significantly reduced by about 90%, and the traditional coding efforts were also reduced. The formal mathematical background of the proposed approach and its correspondence to the conventional control system theory opened us further possibility of the design simulations and formal analysis of this. The interface was due to the simplicity of the implementation of FPGA and an efficient offered and efficiency operations in the form of FSM being successfully applied. The proposed approach offers a promising technique for designing complex and time critical algorithm. Thank you.